Okay, so this is the video for November 5th, I think, hopefully. So we're going to complete this worksheet and then work a little bit on drawing some ray diagrams, drawing angles of incidence and angles of reflection. So the first question is state the laws of reflection. So we're going to write that. The laws of reflection state that the angle of incidence equals angle of reflection, like we hopefully figured out from our activity. So in other words, angle I equals angle R. And the second part of the law states that the incident ray, the reflected ray, and the normal all lie in or on the same plane. That means when you're drawing your incident ray, so if you say this is the surface of the mirror, you have your normal at 90 degrees, you have your incident ray, you have your reflected ray. First law states that angle of incidence equals angle of reflection, so these two angles are equal to one another. The second law states that, so a plane is basically like a flat surface, like the surface of a table, the surface of a board, and we can see that the angle of the incident ray is on the surface of the paper, the normal is on the surface of the paper, the reflected ray is also on the surface of the paper. There's nothing coming out of or going into the paper in this diagram, right? So that's what the second law, the second part of the law means. And next, we looked in class about a little bit about the microscopic view of certain substances, and we also looked at how paper looks under a microscope. You can Google that, just look up microscopic view of paper, and you'll see that the surface of paper is very rough. So it looks somewhat like that. So this is, the surface of paper is not perfectly smooth, even though it may appear smooth to us. I can quickly actually microscopic surface of papier. Yeah, so you can see here that it's not exactly very smooth. It's actually very bumpy and has all sorts of rough and uneven surfaces on it. And so looking at that, we can then speculate that when rays of light fall on the surface of paper like so, say parallel rays of light form, at each of these points there will be a kind of different normal that you will be drawing. And so according to the laws of reflection, the angles will still be the same, but the direction of the rays, reflected rays, will not be the same, because the normal at each point is different because of the bumpy surface. So this is a reflected ray right here. This is a reflected ray right here. And that's also a reflected ray right there. So you can see that they're all pointing in different directions. So this is what is known as diffuse reflection, where reflected rays point in or go in different directions. And this is what causes you to not be able to see your reflection on a surface of paper. The surface of paper is white. A white paper is white, and it does reflect all visible light that's shone on it. That's why it's white. But because it does so in different directions, you cannot see your exact reflection. Another example for this would be like a lake with ripples in it. And the opposite of that, so we're going to compare that to something called specular reflection. And as you might be able to guess, this is where the reflected rays all point in the same direction because the surface is perfectly smooth. So this happens with a lot of polishing, which is required for that mirror, the surface of those mirrors that are made of aluminum or silver that we were talking about. And because it's flat, the normals are all in the same direction, and so the reflected rays are also parallel to each other. Right, we can see that here, and therefore we get a perfectly clear reflection of a person, for example, when you see. So the example of this would be a clear lake or a mirror, the reflective surface, not the glass part, right? The glass part absorbs close to nothing. The reflected ray points in different directions. The examples would be any white surface, like a white wall or a piece of paper or a disturbed lake with ripples in it. Okay. So question 3, we kind of talked about how light rays travel in straight lines, which is very important. And this sort of causes us to kind of perceive things that are not actually there. For example, when we look at something in a mirror, let's say we're looking at our feet in the mirror. So this is the surface of the mirror. We're standing here, and so our eyes are up here. We're trying to look at our feet. So our feet, there's a light source, light shines on our feet reflect that light onto the mirror, which reflects that light into our eyes, right, according to the laws of reflection. We'll talk more about how this happens, but again, we perceive this, so we don't understand, our brain cannot comprehend that light is actually bouncing off the surface and is actually bending here. It thinks that light travels in a straight line, which is why we kind of extend this backward and we see our feet inside the mirror instead of seeing the image of our actual feet, right? We see a virtual image. So there's 2 feet, our actual feet, and then the feet inside the mirror. Okay. Well, again, we'll talk a little bit about this more. There's a little bit more to this diagram, which I'm not drawing as of now. But this is essentially what happens. We have to extend the ray behind the mirror in order to see the image and where it's formed. And we looked at that using a brief activity. So how is an image formed in a mirror? We talked about this is basically how an image is formed in a mirror. Right? We extend, our brain perceives these light rays to be traveling in a straight line, which is why the image is formed behind the mirror. So it's question 3 and the first question 4, kind of the same answer. This is just, again, to understand, I'm not going to ask that exact same question in its current form. And we'll talk a little bit more about how images are actually formed in plane mirrors. So we figured out what some characteristics are. We figured out that the mirror is halfway in between the object and the image that's inside of it. So, and we're going to talk about that more in class. So we're going to jump right ahead to drawing rays. So I'm only going to do one of each like I did in class. The rest will be for homework. So the first thing we're going to do is we're going to identify the surface of the mirror. So we're going to make sure that we take that. So this is the surface. For question number 1, the normal has already been drawn for us, but if you wanted to draw the normal, you would take the point of incidence, which is where the light strikes the mirror. That's our vertex point, so to speak. Right? And you would draw a 90-degree line, and we can see that aligns with the normal. And, sorry, one moment. So we're going to mark our 90-degree angle right there, which coincides with where the normal is already drawn. So that's nice. So now we're going to put our protractor along the normal. Remember, both the incident angle and the reflected angle are measured with the normal, right? So we have to align our protractor with the 0 along the normal and then measure our angle of incidence. And you can see this arrow is drawn along this line. That's where my line was. And we can see that's 60 degrees. It's not 120 degrees because it's an acute angle, 60 degrees. So we're going to mark our angle of incidence, angle I equals 60 degrees. All right, so now I'm going to turn my protractor around because I want a reflected ray. I'm going to put it up here, and I'm going to mark 60 degrees on the outer one. Again, I want an acute angle of 60, so don't go and mark 60. That's somewhere over here. This 60. And then using a ruler or this protractor, I'm going to try and connect these two dots. I don't want that big of a line, so I'm just going to draw towards the direction. And then this angle R is also equal to 60 degrees. So this is the proper way to technically draw a reflected ray on a mirror. So we're going to look at the next case where we're not given as much information. So let's try this one. So again, surface of the mirror would be this surface. First thing I'm going to do is look at the vertex point of incidence. I'm going to mark a 90-degree line over here. That's my 90 degree. And why I'm doing this is so that I can get a normal. So I always need a normal in order to measure my angles of incidence and reflection. So we're going to connect those two, and we're going to call this normal. Then again, I'm going to put my protractor along the normal, and I see that my incident ray is at 10 degrees. So I'm going to mark an angle I equals 10 degrees. So I'm going to turn my protractor around because I want my reflected ray, flip it to the other side, and I'm going to mark 10 degrees again using the outer one because I don't want the 10 degrees somewhere over here. I want the acute angle 10 degrees. And then I'm going to connect that again with a line. It's best to use a sharp pencil. I think would yield better results, but angle R equals 10 degrees. And that's how you draw a proper reflected ray from the surface of the mirror. The rest of these guys are for homework. It's the same. Even if the line is slanting, you still have, surface of the mirror. You align your protractor along the surface of the mirror, and you still draw your 90 degree the same way. So your normal will look slanting as well. That's not weird. That's normal. Haha. Get it? Okay. That's your normal. And then again, measure your angle of incidence, which in this case looks to be somewhere around 42 degrees, maybe 41 degrees. This is 45, so I'd say about 43, more or less. So you turn your protractor around, measure another 43 degrees, somewhere over there. I'm going to connect those two. Like so. So this is law of reflection applied, and here at the back we just have an activity where you have a bunch of mirrors. You start off here, draw normals, draw reflected, mark angles of incidence, draw reflected rays. It's going to bounce here, bounce somewhere over here, I think. And then I think the answer is somewhere on this side. I could be wrong. I'm not going to do that. You can do that for homework, and I will see you in class.